Ladies and gentlemen, the event will be begin shortly. Right now, we have 2 minutes again to continue our plenary session. So we would like to invite you again to take your seat, and then we have inshallah at 10 a.m. Yogyakarta time, we have to continue our the plenary session in this event. Thank you. Okay, ladies and gentlemen, the event will be begin shortly. We would like to invite you, the participation, to take your seat right now. Inshallah, the event will be begin shortly in this event. We will continue the plenary session in this afternoon. Assalamualaikum warahmatullahi wabarakatuh. Welcome back again in the 4th International Biomedical Instrumentation and Technology Conference 2025, everyone. And I think we have already coffee break and some refreshment, and I think we have already spirit again to continue our the plenary session, the 4th International Biomedical Instrumentation and Technology Conference 2025 with the theme Advising Energy Management, Telemonitoring, and Automation System with artificial intelligence to enhance next generation healthcare solution. This session will be moderated by Mr. Insinyur Sisdarmanto Adrinandra, ST, MSc, PhD, IPO. So right now, allow me to introduce to you our moderator in this session, Mr. Insinyur Sisdarmanto Adinandra, ST, MSc, PhD, IPO. Currently serves as the Director of the Academic Development at Universitas Islam Indonesia. His academic background is firmly rooted in electrical engineering, focuses on nonlinear control system and robotic. He completed his PhD from TU Idofund in 2012 in hierarchical coordination control of mobile robots. Through his career, he published manuscripts on control design and sustainability analysis for holonomic and non-holonomic systems, mainly using Lipodov approach. His current research includes the application of mobile robot coordination system as well as the use biological system for control of assistive technology. He is an active member of the IEEE Control System Society, the Robotic and Automation Society. He is currently the active lecturer of Department of Electrical Engineering, the Faculty of Industrial Technology, Universitas Islam Indonesia. So ladies and gentlemen, please welcome Mr. Sidarmantro Adinandra. The stage and the time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone, esteemed guests, colleagues, and distinguished keynote speakers. Welcome to the plenary session of IPTech 2025. We will have 4 outstanding keynote speakers for you today, to all participants. And to ensure that we are on schedule, each speaker will present back to back. So make sure that you hold all your questions and post it after the last speaker, which is Pak Firdaus, complete the presentation. Without further ado, I invite all the speakers to come to the stage, Dr. Ellen Su, Dr. Arifin, and Dr. Firdaus. And also warm welcome to Dr. Masahiro Osa that are joining us online. Please be seated, Dr. Ellen, Pak Arifin. Okay, to make sure that we are on time, so let's start with our first keynote speaker. Our first keynote speaker is Dr. Ellen Su from University Technology Malaysia. She is a distinguished researcher in robotic, AI, and biomedical engineering who earned her PhD from Imperial College London. Today she will present on reinventing healthcare, the power of digital transformation. So Dr. Ellen Su, the floor is yours. Yeah, yes, please. Yeah.
Where's the slide? Sorry. Hello, a very good morning to all, distinguished guests, ladies and gentlemen. So let's wait for the slide. Right. Okay, so my topic today will be about reinventing healthcare, the power of digital transformation. I'm Eileen from University Technology Malaysia. So before I start, may I ask each of you here, if you actually remember when was your last health checkup? That's not bad, really. Many of us, we drag this for many years, right, and never do that. And I want to bring your attention to this because diabetes is actually a very scary disease. 1 in 9 adults is living with diabetes, but the scary part is 40% of them are undiagnosed. They are unaware that they have this problem, okay? And diabetes actually causes 3.4 million deaths annually, right? And it doubles and triples the risk of premature deaths. But what we are trying to prevent is actually permanent disability or amputation, nerve disability, and also blindness. And early treatment can actually prevent all this. So now that we know, why aren't we doing anything about it? Right? Why don't we get checked more frequently? In fact, there are CEOs of organizations sharing that despite being offered the medical checkup by the companies, the employees actually do not take it up. Unless you make it mandatory, the employees do not go for their own checkups, even though paid by the company, right? Because it is inconvenient, sometimes it's painful, and then there is limited data, and it's also very compliance dependent, particularly for diabetic cases. It depends on the person to actually take time and do it by themselves at fixed timing, after meal, and so on, right? So I would like to share with you a very real story. So now that we know about this diabetes issue, there is this particular patch in the market. Instead of using the conventional method of finger prick, urine test, they can buy this continuous glucose monitoring patch and patch it on the skin. You can wear it for, I think, a week up to a month. Then it gives you continuous data. So this is a very real story from my own student, only 20 plus years old. When he first joined UTM 3 years back, he did a health checkup, and it was okay. He was all healthy. But after 2 years, this year, last few months, he suddenly found that he has very, very high glucose level. And when he started using this continuous monitoring patch, he started monitoring his food intake. And he realized that just a wonton noodle, xiao long pao, right? And also Coca-Cola spike his glucose level extremely high, at a very, very high level. But, and this is surprising to me as well, when he take the Diet Coke, it seems that he can keep the level low. I never believed it, but when I see the data, it seems that, that's not bad. I'm not encouraging you to take it, but I'm telling you that the data showed a different result when you take different products, right? So what this tells us is that this type of digital sensors, continuous monitoring, actually can help you monitor your behavior, change your lifestyle. And in a real-world study of over 74,000 population, this continuous glucose monitoring patch can actually help lower blood sugar simply through behavioral changes, right? And then it also lowers hospital admissions. This is one of the many benefits that digitalization and sensors, remote sensors, can help us. So let me start with my introduction, the real one. This is the state of our world today. We have 8.23 billion population in the world, but surprisingly and shockingly, more than half of them do not have access to health care. Right? And Spain is only growing. The World Health Organization predicted that about 10 million global health worker shortage by year 2030. And amid these gaps, we also have non-communicable diseases like heart, cancer, chronic diseases, and diabetes, accounting to more than 75% of global deaths each year. Okay? Actually, the statistics for cardiovascular disease is even worse. It is accounting for 1 death every 2 seconds. But I started with diabetics because tomorrow is World Diabetes Day. And I specially take this to start the session with diabetes so that we are all aware of the risks that diabetes pose, right? And do take action about it. Okay, and health systems worldwide are under tremendous pressure to do more. Right, okay, but what's stopping us? You know, they face immense challenges, and then I'm summarizing it into 4 main areas. The 4 main challenges that is faced by healthcare, that is related to cost, workforce shortage, access and quality, and technological challenges. So let's look at the first one. Very small, sorry. Right. So cost, chronic diseases like cancer, long-term stroke survivors, they have a huge economic burden on the healthcare systems. For example, the statistics for diabetics healthcare costs last year has surpassed USD $1 trillion last year. So the amount is only growing. So we have to try and bring these costs down. And in a lot of governments, in a lot of countries, more than 90% of the budget for healthcare is directed towards curative care. That means they have to take care of patients who are already currently sick or aging, right? And only less than maybe 6 to 7% are used for preventive measures, telling people how to prevent this. And we are trying to shift this condition into more towards preventive, because if everybody is healthy, you don't need to spend so much on curative care, right? And then also, of course, the workforce shortage, the qualified personnel are leaving faster than they are being replenished, right? And then there are burnouts and many issues related to workforce shortage. I think we are all aware of it. And then access and quality. People in rural areas typically has a much harder time getting specialist care, because the specialist has to work with very advanced equipments. It's not that they don't want to be in the smaller hospitals. They need these equipments and tools for them to help make a good and accurate diagnosis. And these are only available in big hospitals. So what can we do about this? How can the rural folks also get this specialist care? Through digitalization, okay? And then also we have technological challenges, because nowadays, I'm not sure about Indonesia, but in Malaysia, most of the hospitals still have their own very siloed database. So you go to one hospital, the data is not shared with others. You go to another one for second opinion. You have to do the whole blood test all over again. More cost, more things to prick, and so on, right? So this is where the power of digital healthcare, comes in. Right, first of all, let's look at what is digital healthcare. It's a technology, I summarize, especially ICT technologies that is implemented at every layer of the healthcare system in order to help improve support decision-making and health services. And how digitalization can help. I also summarize it into four sectors related to just now: cost, workforce, access and quality, and also technology. Let's look at them. So in terms of cost, so for example, we have standardization in different departments in the hospitals, reducing patient care. So if you have blood tests in one department, you don't have to redo it in other places. And then remote patient monitoring, analytics, AI, all resulting in reduced healthcare cost. And we even have claims automation, like robotic process automation, claim system checking your documents by insurance providers. Because of that, they can monitor the claims and then keep the insurance premium lower. Okay, with regards to workforce shortage, now a lot of automations can be implemented, including we start from ambient scribing, where an AI tool can be used to monitor and take clinical notes when a doctor is consulting the patients. So we don't rely on the handwriting, the beautiful doctor's handwriting anymore, right? The AI can take very nice typesetted notes for you, and then can even check whether, the disease and match the prescriptions given. And in NHS UK, they are using AI triage. When you go to the hospital, you take this blood pressure monitor and heart rate and all that, and then they first decide where to send you next. So instead of having a nurse doing that, now they have this AI chatbot doing this. So reducing personnel reliance. And you have command center operations where you have dashboards telling you which beds are free, which beds are going to be free, and so on. So all this helps to decentralize healthcare and using automation. And then you have robotics to deliver medical supplies, deliver linen to the wards, and so on and so forth. And then in terms of access and quality, this is my very favorite, right? You have telehealth, home diagnostics, and then you have AI. Because of all these little monitoring devices that is already deployed, say in rural areas, in clinics, in smaller clinics, we're able to get data and then sending it into a centralized database, improving decision support with AI models. And then you have closed loop referrals. Like some of you submit paper to journal, and then some of us are editors, and then we get reminders, you are supposed to invite reviewers, you are supposed to do this. And then if you didn't send changes, the journal will keep reminding you, hey, you are over the due date by certain things. So this is the closed loop referrals where when patients start to register at the hospital, so the system will track where should the patient be next, and then reminding, this is nurse A, you're supposed to do this part, and there is no feedback yet. So this monitoring can be automated. Okay? And then language and assistive tools, sometimes you need interpreters for people who don't understand the language. Right? And then in terms of technology, we have focus group creating standards that allow everybody in the whole world to follow a certain protocol so that next time we can have all this medical data being freely shared, of course with certain guidelines and governance. And then because we have this digital system, you can implement security actually much better than the manual human person can. You can implement, 2 or 3 tier protocol, who can have access to certain data, who cannot, without relying on manual labor. Okay? And then I highlight 5 top digital healthcare technologies that we can all look at, and perhaps some of us are already working in these fields. So for example, we start with AI and AI. The first one is AI, the second one, electronic health records, wearable technologies, telemedicine, and also just now about data interoperability, right? So some examples of AI, you can start with robotic system doing automatic, tele-operated operations, and then you can have, healthcare management, medical diagnosis with AI, and so on. And I want to share this, personal story. This is some tooth, right? So what can you see from here? Do you know what is happening? There is a crown in the tooth, right? Right, and then swollen. So, of course, I'm not a dentist, so I don't know what is happening. My husband sent this to me, right? He got an x-ray, and then he said this. And then this is what happened. Oops, right? Can you see any problem? Of course, this is from his phone. Can you see any problem? So I, being the clever one, don't tell him, right? Within 1 minute, oops. Yes, right? Within 1 minute, I give him his diagnosis. A long story. And then imagine you even have that picture all annotated with the problems within 2 minutes. And then I asked him, actually, I don't know if these are accurate. And he said, yeah, the dentist said the same. But I couldn't understand. So now he can just ask ChatGPT more without having to pay the dentist fee. Sorry, for those dentists out here. Yeah, right? Is it not working already? Yeah. Okay, so anyway, you are able to, ChatGPT helps me see things I cannot, and also help us to understand, right? Now they can tell me exactly what is happening. Okay, and then of course we have the electronic health records. We cannot, I cannot tell you how important it is. In all the metrics, in a lot of the metrics that we measured, it reduces hospital deaths, it reduces the requirement for duplicate test procedures because now you are sharing data, you don't have to repeat tests. It is improved continuity, disease management, near real-time monitoring, and a country, through a study, it is said that a country implementing interoperable electronic health records could save thousands of lives annually, reduce healthcare costs by billions, and improve patient satisfaction. And in fact, I think one of the very successful ones in Singapore in 2011, they already have this national health record, right, system. So 90% of their hospital data are all interconnected. And this month, November 2025, they tabled a bill to mandate even the private hospitals to share their data into the same system. So now everybody in Singapore, as long as you go to the one of the hospitals to take, do a medical checkup, your data is available everywhere else, okay? I think that's something we can learn from. And then, of course, telemedicine. These are some of the, and then sensors. We need sensors in the system to give us these digital signals. We need, for any digital system, the sensors is very important because it provides us the data, right? And then I think a lot of us are working on this. And then we have telemedicine, we have companies providing virtual patient monitoring, some have chronic patient management and so on. These are providing different services. Virtual doctors, they have systems where you do doctor visit through videos just now. And then also the data platform interoperability. This one we have new standards, the FHI to HL7. So this one focus on mobile applications, cloud-based, because now our data is going to cloud, so they are coming up with protocols, so the whole world can share the data, seamlessly. So having said that, am I doing on time? So I will highlight some of the related projects that we have done in UTM. We recognize that building a truly connected and smart healthcare system is a massive multidisciplinary effort. We can't possibly do all, so we only do a part of it a little bit, okay? I will highlight some of the work on wearable devices and then some of the work on AI that we did. I want to start with this company called TechCare Innovation. It is very special because it is started by one of our students. A group of our students from their FYP project, they started with upper limb rehabilitation robot, right? And then it goes on to become a PhD work where they deployed it to the stroke survivors. And then they realized that in a lot of homes, you don't have enough space. So they make it smaller and make it modular so you can train the fingers, and they start a company commercializing this. And this is how it looks like here. We don't have time for video. And then the company went on to also build more digital products. For example, games that can train mental alertness, and it gives different difficulty level. And then improving on that games, they do this interactive board. Instead of having motors just now for patients who can move their hand, they even do this interactive board where they measure the range of motion, then also the response time, okay? And then also TechCare driving simulator. This is a work between the hospitals and the requirement from the Ministry of Transport in Malaysia. Because we do have very elderly individuals who are still on the road driving, but we actually don't know if they are fit to drive. Also maybe stroke survivors. So what they need is assessment tool, so you can assess if they are fit. And on top of that, you can also train their reaction time in a safe, simulated and controlled environment. So this measures response time, coordination, and cognitive measures. Okay, and I move on to Feebot. This is also a product from the same group of students. This is also a product from our students, also final year project, went on to join competition. They went on, sorry. They went on to, oops. Yeah. Okay, so this one, I forgot where am I? Okay, so again from the students, and then we further work on it with a research study, comparing the data from this digitalized platform versus the conventional test, and we find that the Feebot scores actually correlates quite well, and it is a more sensitive alternative actually with quantifiable data as compared to standardized tests. Okay, and then we also work on heart arrhythmia, detecting the heart rhythms. We have mobile apps for it, and then web applications. I go very fast, don't worry. And then we put in analytics into it. So the idea is to provide real-time notification, connecting rural healthcare, because it's very difficult for them to stay in the hospital for days to be hooked up on that Holter systems, okay? And then we went on to extend this project further into a PhD work where we try to not just detect whether an arrhythmia has happened, we try to predict before it happens. So we have the onset research for ventricular arrhythmia, because when it's ventricular arrhythmia, the time span that you have for doctors usually is very, very short. So we did one study using statistical methods, right? And we are able to extract, just using one feature, we are able to predict the onset at 90% accuracy 4 minutes earlier before it happens. And we also attempted a different method using heart rate prediction method. So we take 10 minute signal and we move the signal further away from the onset using heart rate variability prediction. This is using machine learning, SVM, right? And we can get over 89% accuracy with an earliest prediction time of 77 minutes here, right? So with the statistical method, you get shorter but slightly higher accuracy. Okay, and then we have diabetes monitoring, the topic of today, right? We also try to see if there are other non-invasive methods to monitor diabetes. So we try with using acetone gas level, because it has been shown that for diabetes, when glucose level increases, the acetone level also increases. So we built this, and then we tested it in the lab. For the diabetes work, it is still a lab validation with glucose solution, right? So we build systems with apps, and we have matched the diabetes level with actual measurements. And on top of that, another method, instead of gas, we use near-infrared spectroscopy, right? 3 different LEDs, and then we also detect it based on glucose solution, and it gives very good prediction. We are yet to test this with human subjects, so this is a work in progress. And then we have AI works on brain disease classification using different models, and then we have lung disease classification using AI. And then also we continue to work on heart arrhythmia, because now we have deep learning models. You can do many types of arrhythmia detection. And finally, this is already last, right? So we have virtual reality for surgical skill assessment. So we build training models, different settings, and we monitor the surgical skills for micro accuracy. And then, I hope this is working. So we have this needle grasping, we put visual cues, and then we also, because it's a haptic system, we can actually put error amplification. We push their hands so that they are less accurate, and because of that, they need to train to be more accurate. And then we test them using this needle insertion module, right? And then we can measure the accuracy. So using this system, we are able to extract features that can differentiate a competency level of somebody. And the system can predict, are you a surgeon with many years of experience, or are you non-surgeon with no experience level working on microscopic tasks? Okay, so that's the end of my presentation. Wait, right? Okay, so I believe that the digital revolution is shifting healthcare from reactive systems to more proactive, personalized, patient-centered experience, decentralizing the healthcare system, and then we aim to shift curative care to more preventive care, right? So to end this, I think research with a purpose, we try to transform, our team is trying to transform digital tools into better care for the society. Thank you very much.
Okay, give warm applause to Dr. Eileen. Thank you very much to be very punctual, Doctor. Okay, so our next speaker is Dr. Ahmad Arifin from Institut Teknologi 10 November. He will give talk about intelligent rehabilitation and assistive system, a route to improve quality of life. For your information, Dr. Arifin is, in the past, was the head of the Department of Biomedical Engineering at Institut Teknologi of Surabaya, which is one of the oldest biomedical engineering department in Indonesia. So I believe that his talk about this assistive technology will give us more knowledge about what happened now in Indonesia. So Dr. Arifin, the floor is yours.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning, audience that joined in offline meeting. Also, good morning for the audience joined in online meetings. I'm Ahmad Arifin from Institut Teknologi 10 November, Surabaya. My speech entitled Intelligent Rehabilitation and Assistive System. A route to an improved quality of life. Of course, this address to the quality of life, address to paralyzed or such kind of the impaired subject. Okay. this information about my university, ITS with maybe about 4 or 5 campus in Surabaya, and I'm from Biomedical Engineering departments. That my departments emphasizes in developing application of the science and technology to medical sciences, and one of the exposure is in rehabilitation and assistive technology. Some document summarize the type of prolonged history of the ITS curriculum in electronic engineering, emphasize in development of the technology to assist and also to rehabilitate the subject with disability. And the core field of the biomedical engineering in our rehabilitation and assistive technology refer to the definitions provided by James Reswick in Society of Engineering in Medicine and Biological Society, that rehabilitation engineering focus to build or to improve the handicap or individual with disability, but assistive technology that have the strong relationship between rehabilitation engineering and assistive technology, focusing in how to improve the function in order to access or in order to improve the existence in society. And our focus in motor system, so that if we learn about the control in living tissue, in generating such kind of the muscle force, etc., actually this involve of the motor system in touch, that in our motor system, command of the neural signal issued by the central nervous system is implemented the inserting of the muscle force in our skeletal muscle, so that for the normal subject, such we can do the functional movement, riding a bicycle, running, hiking, etc. But in case of the subject, is such ability absent due to the in-touch control system for the brain to the motor to lower motor neuron is absent. So some the condition is the motor disorder. The motor disorder can be occur when the absence of the control commands due to the damage on the brains will produce the absence in the upper motor neuron and also in the lower motor neuron. But in the case of the spinal cord injury, that the absence due to the absence of control to the spinal cord injury. And based on the location of the neurons in our vertebra, so that some of the disorder of the movement, some dilation of the movement is different. And as a part of the rehabilitation engineering field, we have such a method in order to ameliorate, in order to restore, by utilizing the artificial electrical stimulations. FES, functional electrical stimulation, is a method to restore of the functional movement by utilizing the external electrical stimulations in order to change the absence of the control signal. By this external control system, the muscle force can be reproduced. Utilizing the external control system should be considered how the natural function of the control signal from the brain, so that in this field we should consider deeply about the anatomy and also physiology of the movement. FES actually applied to the restoration of the two kind of the movement. So the goal-oriented movement, such as the movement of the hand, arm, that the control action related to the endpoint or the goal. And the next one is this cyclic movement, such as the walking, running, standing, and sitting down, it is the cyclic movement. We should consider of the sign behind this movement due to the different orientations between the goal-oriented and also the cyclic movement. And the object of the FES can be recognized for two groups. One is the functional restoration. Though this objective is in order to utilize the programmed and repeated electrical stimulations, yeah, in order to ameliorate, in order to restore again the loss of the functional. So the effort is the long time in order to have the effect of the therapy or rehabilitation. And the next one is the therapeutic effect in order to improve the volume of the muscle force and also to reorganize the sensory and motor system, such as in this picture provided by the Tohoku University FES and I group, led by Professor Handa at the time in 2000 year, that improving, yeah, the left hand is the before due to the rehabilitation by functional electrical stimulation, and after having the 3 months of the electrical stimulation, improving the mass of the muscle and also the volume of the muscles. So that's all the evidence that FES can restore the basic idea about how to restore the motor system. And by using the program and also repeated, the functional restorations can be reached by using the control. And it is the story about how to improve the FES using the control, using the closed loop control system, route toward the better quality of life through the knowledge engineering approach in developing cycle-to-cycle control for FES industry. Good. So that this the speech about the how to establish the method, basically to show the evidence effectiveness in the context of the control system using the closed loop one. Because of we have the evidence that restoration of the paralyzed get by FES actually is very high niche. There are a large number of the paralyzed subject, but the improvement should be in realizing the closed loop control. For example, if they're in preventing foot drop, for example, in order to avoid stumbling gait, so the fall, etc. And also, subject actually hope about the controlling swing phase. So restored gait actually focus in controlling swing phase, because of during swing phase we have forward propulsion. If we have forward propulsion during we have such kind of problem about the FES control design, about the characteristic of the our motor system, the non-linearity, also the problem of the diversity about the one subject and the others, and also for the time by time characteristic. And the one most important is about the muscle fatigue, because human is not machines, so that fatigue is avoid our progress. And in this case, we should consider about how to manage the method so that we can adapt to the muscle fatigue. And the current clinical method is using the open loop system, but the closed loop control even expected, but improvement is limited, so that we should get more and more idea. Closed loop control not actually ready in clinical use because of the acceptability is questionable by the clinical, so that we should combine about the method in neuroscience, method in medical approach, method in the therapy, etc., to the automatic one. And one of the method that tested in simple is the cycle-to-cycle control, controlling the joint angle trajectory in one cycle, and then apply this deterioration, apply this error, etc., in order to improve one for the next one. This method is actually hope to apply to the clinical, but we need such kind of how the evidence, and also we should show the method is safe to clinical applications. My method is utilizing the approach in artificial intelligence, in intelligent system by means of the knowledge engineering approach, or the KE, or expert system, so that this step is including the task definition, knowledge acquisition, knowledge representation, and also, of course, at the last is to you can understand about how to develop the practical and also the test in order to have the evidence. And task definition, we learn about the movement science, anatomy and physiology of the gait, relationship between the force and also the physiological process, etc., in order to realize the one. Next is the knowledge acquisition, the process of the how to measuring, to develop the database, and also how to get the relationship into the practical one in the microcontroller to control the control parameters. And the next one is the knowledge representation, how to compresses the knowledge already taken during the data acquisition in the format of the electronic one, format of in the hardware and software, etc. And lastly of the step is the how to implement in practical. So I realized cycle-to-cycle control approach in context of the physiologic, so realizing in the physiologic controller, so that the control method is realized in the fuzzy rule, so that this can be realizes the idea how to improve the performance of the PID control that for the long time realized with the deterioration in controlling the system that have the diversity among subject and also for the long time. And this is one of evidence about the testing of this method using the multi-joint movement model, and the trajectory we can see here that the trajectory already realized correlated to the normal pattern, and also the settling index by mean the parameters of the controller can reach the target within the small value. And the next etap, the next route is about the how to realize this one in practical control. This page tell about our step in order to realize multi-joint control is step by step using the single joint, for example, in testing of the knee joint control. So preparations about the muscle, and also design of the practical controller using the standard FES, yeah, also using the personal computer as the part of the realization of the physiologic controller. The result showed that in knee extensions, larger error within the 5 degree, yeah, joint angle can be realized in the small numbers, and also the bus duration stimulation can be automatically realized. This is the same character with the basic study using the multi-joint model of the human gait in the case of the hemiplegic gait. And also when the muscle is fatigued, so that in this result of the subject B, we can consider the process of the physiological fatigue occur, even the bus duration increase, so that the maximum joint angle can be realized, so that the physiology can realize. Improving of the control capability has been considered and realized by two main functions of the adaptive method. One is the error base, yeah, by mean the error based output adaptation function, EOAF, and the second one is the using the sensitivity who related to the sensitivity or the stability of the joint angle or the maximum joint angle or target. So it is the one example. Could you please enter this page because of the video? Yeah, start the video. Yeah, so that the artificial signal that as a rehabilitation method produce the contraction of the quadricep muscle in this video, and also the hamstring one to produce the movement of the knee flexion to reach the maximum target, and also the knee extension to maximize the knee extension movement. For example, it is important, for example, during our get to reach the maximum knee extension before we initial contact. Yeah, can pause or end next. It is the control realization evaluations, so that the maximum joint angle and joint angle of the knee flexion and also knee extension could reach practically, and also can be accepted because of the number of cycle to reach the condition automatically realized by our microcontroller, and also bus duration stimulation can realized in the context of the higher improvement when the error is large, and also the smoothly improve after reaching the target. And the evidence that practical controller realized the basic study, so that the model we utilized during the basic study and also the control algorithm is actually well done, and also could be safe in the context of electronics, and also in the context of the control system. So this framework captured through the knowledge engineering approach and also realization of the cycle-to-cycle control for multi-joint was easy. It is one the method in the easy method to establish the evidence and also to propose for the clinical application. Capability of the fuzzy FVS control could control multi-joint movement in the context of the cycle-to-cycle control, and also the realization of the fuzzy control for multi-joint movement by the experimental test in the real gait movement will be the further topic. This is the one idea how to improve more affordable. Because of the idea of the affordable, we should consider how to realize this one more possible to improve in rural, especially in Indonesia. We have such kind of the problem in realize the more affordable instruments, yeah. Because of electrical stimulation in the previous study was standard, the big one, not wearable, and also joint angle sensor actually very high cost. So that the development in the wearable system is very crucial. First step is the utilizing low-cost sensors such as the gyroscope and all the low-cost accelerometer, and we utilize the Kalman filtering. So we need learn about the Kalman filtering algorithm, and the evidence that we compare with the publication in standard of rehabilitation engineering provided by Jacqueline Perry, and also my study, the previous study of the development of movement database, yeah, and the left one is the proposed method, so that the result of the character of the low-cost sensor is acceptable in the context of the movement science. And then the realizing of the cycle-to-cycle control for multi-joint movement. So it is the real wearable one, the first generation of the ITS system for cycle-to-cycle control in low-cost and also wearable system. And then please enter the video. So we tested with the simulated normal subject, simulated the hemiplegic gait in order to test the performance of the control performance of this. So we can see how knee and ankle joint can realize maximum joint angle by mean the target of the control. The left side is the without FES, and the right one is the with the functional electrical stimulations. And the next one, we extend to the movement of the two joint movement by mean of the multi-joint movement, hip and knee joint. Expand the instrumentation for the multi-joint by mean the multi-channel both stimulation and also for the sensors. And it is the next video is the controlling multi-joint movement by simulated hemiplegic gait in the left one. And in the next page, it is the realization of the joint angle. So that in the middle one is the simulated hemiplegic gait without stimulation, but successful to reach the target in the maximum flexion and extension, both hip joint and knee joint realized well in FES by cycle-to-cycle control. And this one, the evidence how the physiologic controller can realize the stimulation bus duration, so that increase until they successfully meet the target, and also how this result have the evidence that this meet to the basics studies about the multi-joint controller. So that's the how to have the evidence one in the multi-joint controller. And the next one is the establishment the basics capability in upper limb joint. Yeah, it is the example of the wrist joint control. Yeah, and also development of the FES can also be hybrid between the FES and also controlling joint movement by using robot. So it is the example of this robot. And it is the method of the hybrid system. So we control the movement of the joint of the upper limb by robot, and also combining with the method of the FES by using the realization of the FES and exoskeleton hybrid. So by using this method, we can see the stimulations together with the movement of the robot in order to have the therapy for the subjects simultaneously by using the closed loop FES. And the next one is the assistive technology, so that for the disabled person with the impairment of the motor system, we develop the wheelchair in order to improve the our welfare to the subjects using the joystick, and also for the convenience, we also explore the possibility of utilizing such kind of the control method for the possible difference velocity for one subject to the other subject. Yeah, first one is using bioimpedance, for example. We can see the video for this one. Clicks, yeah, start for the video. By using the commands for the bioimpedance, by utilizing the injected, yeah, small current, very small current and low voltage to the subject in order to detect the command for the subject, encoded command to the controller. Okay, we go to the next example. The other one is the user control using electromyography, so that we can consider utilizing EMG signal is suitable for the person with disability for the lower limb, but upper limb is still in touch, and also for the elderly it is possible. And we tested in some the method to start with the stationary position and then to follow the trajectory to reach the certain speed using the subject normal subject simulated for the hemiplegia and others. Okay, the next one, it is for the standard sign language of Indonesian by mean CB. We have this standard translation for subject with the difficulty in communication, such as the hearing and also impaired individual. Using the CB, we can translate such communication using the alphabet A, B, C, D, etc. And then we establish the sensor system and also the method of translation using the standard text-to-speech, etc. So we can test it by use the translator of the alphabet and then compose to the words. And the next one is this is the one example during the testing. So for the word of in bahasa kata, so the KATA, KATNA in Indonesia can be successfully recognized and then transform to the word as the kata. So it is possible to improve the communication, quality of communication between the hearing and also speech impaired person with the normal subject. So difficulty using the translator, the natural translator is very difficult to accept to the normal subject, so that we can assist the quality of communication. Also for the difficulty of the learnings, we also develop the prototype of the assistive robot in order to improve the focus of the student with disability in difficulty of the focus. With the sum of the evidence difficulty in order to develop and also the difficulty in order to reach the better acceptability for the user, also for the practical. So the purpose system affected the student patient for the learning, focus, and finally, of course, the improved learning gain. But the difficulty is to understand the focus and also to the mode of the student with cognitive impairment. So in order to realize the level of learning, the difficulty of the learning, and also to realize the user interface is the step of the research that take long time in order to meet the subject characteristic. And we also should learn about the method of delivering education. So the partner in Faculty of of education is very important. I think UEE also have the Faculty of Education and maybe can also join this idea and etc. for near future. That is the conclusion that in the field of rehabilitation engineering and assistive technology, the effort have realized a route toward the improved quality of life of the person with disability. Okay, thank you very much, and thank you very much for the UEE leader for the complete committee of this seminar. I joined the first IB Tech and I joined today as the keynote speaker, and very good example of the collaborations in the national university because of ITS and UEE have the good relationship until now. Thank you very much.
Okay, give warm applause to Dr. Arifin. So his talk is more about the assistive technology, and as you can see, some of them are become the proudness of Indonesia. So our next speaker is Dr. Masahiro Osa. Hello, doctor. Can you hear us?
Yes, I can hear you.
Thank you very much. So Dr. Masahiro Osa is from Ibaraki University, and he has 10 years of experience developing magnetically levitated actuators for mechanical circulatory support devices. So his talk today is about advance in magnetically levitated motor technology for the next generation pediatric implantable rotary blood pump. So doctor, the screen is yours.
Can you see my slide? Excuse me.
Yeah, we can see your slide.
Okay, thank you very much. Thank you very much, and good morning, ladies and gentlemen. I'm Masahiro Osa from Ibaraki University. So it's great honor to speak here, great conference today. My presentation title is Advances in Magnetically Levitated Motor Technology for Next Generation Pediatric Implantable Rotary Blood Pumps. My talk is about how artificial heart technologies have evolved over the past decades, and from early pulsatile pumps to modern magnetically levitated devices, and how these advances are shaping the future of pediatric circulatory support. So it start at the beginning of my presentation. I will introduce myself shortly. I'm Masahiro Osa from Ibaraki University, and I'm PhD on newly proposed. I got a PhD on a newly proposed 5 degrees of freedom active control concept of double status self-bearing motor, and graduated from Ibaraki University in 2014. And I have been assistant professor of Ibaraki University in 2014. Then from 2022, I was a lecturer and so on. And I'm now assistant professor. So I'm engaged in development of magnetically levitated motor for ventricular assist device rotary blood pumps. Specifically, I'm promoting miniaturization of the maglev motor for ventricular assist device and self-sensing drives of the motor, and evaluating the rotor dynamics of magnetically levitated motor. I'm mechanical engineer, not surgeon. So this is outline of presentation today. I'll begin with history of artificial hearts. This is a heart pump, and the move to pulsatile flow pump and continuous flow pumps, followed by the discussion on bearing mechanism and magnetic levitation, and finally introduce our project, pediatric ventricular assist device development, before summarizing my future perspective. This slide shows a history of artificial heart development. The concept of an artificial heart began nearly a century ago. In the 1930s, Karel and Lindbergh created a perfusion pump to keep organs alive outside the body. Later in 1953, John Gibbon developed the first heart-lung machine, which made open heart surgery possible. There was the very first step toward mechanical circulatory support. In 1969, Liotta and DeBakey implanted the first total artificial heart in human patient. A major milestone followed in 1982 when the Jarvik 7, as shown here, became a first long-term total artificial heart used clinically. These pioneering efforts provide mechanical support could sustain life even when the heart completely failed. However, replacing entire heart was extremely challenging. So researchers shifted focus on total replacement like this to ventricular assist device. This is a bypass. This pump creates a bypass flow rate with a rotary blood pumps or pulsatile flow pump to assist the remaining heart. This gave rise to ventricular assist device or VAD, which supports the heart's natural pumping function instead of replacing it. Over the next decade, ventricular assist devices become smaller and more reliable and more energy efficient. Their clinical role expanded from bridge to transplant to destination therapy. Destination therapy is a long-term use of the ventricular assist device. Long-term support for patients who are not transplant candidates. This evolution set the stage for today's continuous flow technology. Early ventricular assist devices tried to mimic the natural heartbeat. They used flexible diaphragm like this. This is a blood chamber, and this is a pneumatic or oil chamber. They use flexible diaphragm and mechanical valves driven by pneumatically drive or electrically drive to create pulsatile flow, much like real ventricle. The advantage of the pulsatile flow system was as shown here, right here. They produce physiological pressure and flow patterns. And clinicians found them familiar and easy to monitoring. However, these devices were bulky and mechanically complex and prone to wear and failure because a lot of moving part is included in the pulsatile flow pump. The large and also large external console and noise operation mode them unsuitable for long-term use. And risks of thrombosis formation and infection at the blood chamber and penetration tube, penetration skin with the inflow and outflow tubes, and low durability and patient quality of life. These limitations motivated researchers to explore simpler, more compact designs, leading the development of continuous flow pumps like this. Continuous flow pumps take a completely different approach from pulsatile flow pumps. Instead of beating like a heart, they generate a steady state flow of the blood using the rotating impeller, either axial flow pumps and centrifugal flow pumps. These pumps are simpler and much more durable with fewer moving parts and continuous rotation. They offer high reliability and low mechanical stress, enabling long-term support even for outpatients. And this is summarized advantages of the continuous flow pumps. Continuous flow pumps, simpler mechanism and mechanical reliability and device. It can be implanted inside the body because device size becomes smaller than pulsatile flow pumps. However, continuous flow pumps still face key challenges. Mechanical bearings causes friction and heat to suspend the rotating impeller, which can lead to hemolysis and thrombosis. And eliminating mechanical contact becomes the next technology goal, which bring us the magnetic levitation. There are the clinically available devices in Japan, devices like HeartMate 2 and HBAD hardware and HeartMate 3. This represented milestone in the evolution. Each generation becomes smaller and more efficient and capable to supporting patients for many years. Our bearing system are essential to support the rotating impeller. There are the many types mechanical. Main types is mechanical bearing, and next generation bearing is hydrodynamic bearing and magnetic bearings. Each offers trade-off between simplicity and durability and biocompatibility. Let me show the several types of bearing to suspend the impeller. Here is mechanical bearings. Mechanical bearings are compact and easy to manufacture, but they roll in physical contact, causing wear, particle generation, and potentially damage to the blood cells. This is a video of the mechanical bearing using the blood pump. Here is a pivot bearing to suspend the rotating impeller, and blood flow is right here. So yes, blood flow is generated from here to here. So mechanical bearing has a risk to generate thrombosis and hemolysis. And next slide shows the hydrodynamic bearings use a thin film of the blood to support the rotor. This technology is used for hard disk drive, and this reduces contact, but stability depends on the flow condition. Flow condition is related to the rotating speed of the impeller. So low speed rotation, the hydrodynamic effect is deteriorate, and then the hydrodynamic bearing is cannot be used for low speed blood pump. So the rotor may contact the housing during the startup to low flow rate. And this slide shows magnetic bearings. This is a main topics of my talk. Magnetic levitation eliminates these issues by suspending the rotor in the magnetic field. Active magnetic bearing control rotor position using electromagnets and the sensors. While passive element means non-regulated axis. For example, one axis direction control pumps, the passive stabilization axis is X, Y, and theta X, theta Y. So we have to choose the actively controlled axis by using electromagnet to suspend the rotor. So this is trade-off between the device size and the stability according to the actively controlled axis and the passively stabilization axis. The magnetic levitation technology can completely contact-free rotation. Several commercial devices now use magnetic levitation like HeartMate 3 or Biomedical in China. These systems show excellent long-term durability and reduce hemolysis and thrombosis. In short, magnetic levitation offers zero mechanical wear, improved hemocompatibility, and greater reliability. These features makes it especially promising for small and long-term pediatric ventricular assist device. This is a video of the magnetic levitation. Center part is the floater, and this is levitated. As you can see this here, so space from between the stator and the rotor. This is a blood flow clearance. Then the blood pump, magnetically levitated blood pump, has the biggest advantage of low hemolysis and thrombosis. This is a magnetic suspension system. We have to use a feedback loop system because magnetic system has negative stiffness, as shown in these graphs. Negative stiffness is inversely proportional to the displacement. Blue one is conventional spring force. This is the positive stiffness. So inversely relationship between the spring force and the negative stiffness, then negative stiffness characteristics in magnetic levitation motor makes the dynamic system unstable. Then we have to use active magnetic bearing control rotor position using electromagnets and sensor with a feedback control loops. Now we are developing a magnetically levitated blood pump and for pediatric patients because so we are miniaturizing the magnetic system and the blood pump system. And this is the motivation of pediatric security support. A pediatric ventricular assist device is used for bridge to transplantation and or bridge to adult ventricular assist devices. However, X-Cup pediatric is only clinically available ventricular assist device in the world like this. This device is very good device for pediatric circulation. However, only 160 pediatric patients in each year receives treatment using these blood pumps and have several risks of thrombosis formation and in the blood pump and infection at the skin penetration site of the inflow and outflow. Larger tube diameter have larger tube diameter. So implantable and continuous flow ventricular assist devices are strongly required for pediatric circulatory support to overcome potential risks of the pulsatile flow ventricular assist device like this. Now we are proposing the rotary ventricular assist device like this. The specification of the proposed device is listed here. The pump flow rate is around 0.5 liters per minute to 2.0 liters per minute. This is relatively low flow rate compared to the adult patients because small patients has small volume blood volume and head pressure of around 80 to 120 millimeters of mercury, and the pump speed is estimated to 2000 from 2000 to 55,000 RPM. This is a schematic view of the proposed ventricular assist device. This is a very simple structure. just two identical motor stator and levitated impeller. Impeller is the only one moving part in the pump chamber. And yeah, I'll show the video again. This is rotor impeller right here. Then the magnetic levitation and the rotation. So blood flow is created like this. And here is a suspension and principle of the proposed device. Firstly, I'll show you the axial position control mechanism. The levitated impeller has a permanent magnet on the surface of the levitated impeller, so the axial suspension force is generated right here. And then electromagnet regulates magnetic field in upper side and bottom side. For example, in this figure, the top stator produced magnetic field to get the field strengthening, and in contrast, the other side stator produced magnetic field to get the field weakening. So magnetic suspension force imbalance is occurred like this. Then axial attractive force can be available and can regulate the levitated impeller in the pump chamber. Next one is the inclination angle and radial position control principle. The inclination torque and the radial suspension force can be produced independently with double stator mechanism. This is inclination torque production, and here is the radial suspension force production principle. 4-pole rotor permanent magnet generates north pole, south pole, north pole, south pole. In contrast, the stator electromagnet produced a 2-pole, south pole and north pole. In left side, north pole and south pole is facing, so the attractive force is available. On the other hand, the right side, north pole and north pole is facing, so the repulsion force is available. Then we can get the rotating torque around the radial axis. The radial suspension force can be available independently with the 2-pole magnetic field in this theory. This is restoring torque production principle. When the upper side motor produces clockwise restoring torque, and the bottom side is also generating the clockwise rotating torque, the radial suspension force is cancelled each other. Then the only restoring torque can be available in this magnetic field. This is a control system, a schematic view of the control system of the magnetically levitated motor for pediatric ventricular gaseous device. 3 eddy current sensors are set on the stator slots to detect the axial position Z and inclination angle around the y-axis and x-axis. And whole element sensors are placed on the stator slots to detect the rotating angle of the impeller. And this is a feedback loop system, microprocessor using D-Space software implemented in the digital PID controller. And power amplifier excites control windings to regulate the impeller position and the rotating speed. This is a prototype pumps to use bench test evaluate the basic characteristics of the hydraulic performance and the magnetic suspension performance. So we fabricate the pump housing with plastic pump. And this is a closed loop circuit to mimic the body circulation system. Here is a pressure gauge, and here is a flow meter to evaluate the pump hydraulic performance. The pump was driven at a rotating speed of around 3,000 RPM to produce the pediatric circulatory support. And here is the hydraulic performance of the developed pump. The pump can produce a flow rate of around 0.5 liters per minute to 2.5 liters per minute. It is suitable for pediatric circulation. And this is the power consumption of the developed pump. Power consumption is around 1.5 to 2.5 watts. This is not so high to get a temperature rise. So this indicates biocompatible blood pumps. This is magnetic suspension performance. The blood flow clearance is 0.3 millimeters. Then in these graphs, the plot reached at the upper limitation, the impeller is touching at the casing. So as you can see this figure, the impeller is really stably suspended with the magnetic system to have margin of the blood flow gaps. This is indicating the low hemolysis and low blood clotting. And this is a radial displacement. It's time to close, so I'll skip to this slide. And this is shock durability testing. We are using shaker to have disturbance to the pumps. The pump can achieve 5G shock resistance. And we are trying to in vitro testing and animal trial of extracorporeal circulation. We can get the results of low hemolysis property compared to the commercially available pumps, and more than 30 days perfusion of the blood flow outside the body. And this, as you can see this figure, there is no thrombus formation in the pump. And then we try to fabricate the prototype device for chronic animal trial with implanted device. Then we investigate the pump material, housing material, and shape of the blood pumps. We change the material from resin to titanium to implant the pump, and outer shape of the blood pump is redesigned for improving anatomical fitting. And this is a video of the blood pump operation in the water to mimic the inside the body operation. Now we are trying to enhance the anatomical fitting further, so we try to reduce the height of the blood pump and enhance the magnetic suspension force and torque by changing the geometric parameter of the magnetic circuit like this. And now we are starting the pilot animal experiments with goat, and this is a result. 25 days circulatory support can be available at the flow rate of 1.5 liters per minute and rotating speed of 30,000 RPM. This is estimated pump-driven condition. A non-contact pump operation with full magnetic levitation can be available, and no significant temperature rise can be available in this experiment. So it's time to conclude my talk. Let's look back at the journey. So from pulsatile pumps to continuous flow system, and now to magnetically levitated designs, total artificial heart ventricular assist device technology has continuously evolved to improve both durability and biocompatibility. Looking ahead, the next challenges are fully implantable system, wireless power transfer, and long-term pediatric applications. Our ultimate mission is to create heart pumps that can grow with smallest patients and restore normal life for children with heart failure with magnetically levitated compact ventricular assist device system. That's all. Thank you very much again.
Okay, thank you very much, Dr. Osa. Okay, let's give Dr. Osa a big warm applause, everyone. So I hope you are still on, because this is starting to have a hard time. I see some of you are already a little bit fell asleep. So we start with digital transformation in healthcare, and then continue with designing of assistive technology, and then we continue with how we can replace our heart. And this is very nice to myself, that knowing that mechanically there is existing solution for that. Okay, our last speaker is, we call it Pak Firdaus. He is our head of department of electrical engineering. To be honest, if you know him, his background is more on telecommunication technology, but one of his expertise is bringing technology into commercialization. And today we will talk about challenge and enabler in biomedical technology commercialization, insight from academic and industry collaboration. So Pak Firdaus, the floor is yours.
Okay. Thank you very much, Pak Nandra. I have 10 minutes before we break for lunch. But we still have Q&A session. Okay. Ladies and gentlemen, distinguished college, good afternoon. It is a pleasure and honor to serve as the keynote speaker at IBTech 2025. Today, I wish to share reflection and learn from our team journey in bringing university-based biomedical instrumentation and IoT innovation into the market. Okay. Specifically, I will comment on two successfully commercialized product. First one is Algis IoT, an alarm system for medical gas pipelines in hospital. And then our IoT-based modular operating theater, MOT, automation system. My goal is to contribute practical insight into how research and innovation can be translated into sustainable product in the medical device domain, especially in Indonesia and other emerging market. Okay. Globally, the medical device industry continues to expand rapidly. You can see on the slide, value at around 500 billion USD in 2023. It is projected to reach nearly 900 billion USD by 2030, representing a compound annual growth rate of about 8.4%. This growth is driven by technological convergence, aging population, and digital transformation in healthcare system worldwide. In Indonesia, the trend mirror this global momentum. Our national market is estimated at approximately 4.7 billion in 2024, but yet more than 80% of medical devices used in hospital are still imported. Okay, this dependence highlight a strategy gap and at the same time, a tremendous opportunity for locally developed technologies. With the increasing adoption of Internet of Things solution in hospital infrastructure, the door is wide open for Indonesian innovator to design smarter, connected, and affordable device. Local innovation in biomedical instrumentation not only addresses national health system needs, but also strengthen technological independence and industrial competitiveness. Okay, this is our first product, Algis IoT. It was developed to solve a real problem in hospital, that is the lack of early warning for medical gas failure. Many hospitals still use analog local alarm that could not notify staff quickly during a pressure drop or leak. We designed a digital IoT-based system that monitor gas pressure and flow in real time, send data to a central dashboard, and issue alert through mobile notification. Beyond safety, it is also enable predictive maintenance by tracking gas usage trend and detecting anomalies early. Today, Algis IoT is installed in several hospitals across Indonesia and has proven that academic innovation can lead to a market-ready, high-impact product for hospital infrastructure. This is our second innovation product. Our second innovation is an IoT-based modular operating theater automation system. In many hospitals, air quality, pressure balance, and filter condition in the operating room are still controlled manually, which risk contamination and inefficiency. And then we developed a smart monitoring and control system that continuously track temperature, humidity, air pressure, air quality, and filter usage. The system integrate with AHU, provide visual dashboard, and trigger alarms when filter replacement or air imbalance occur. This innovation improve sterility, energy efficiency, and patient safety, and show how IoT can modernize hospital infrastructure with practical and affordable technology. Okay, the first key principle is to start from a real problem that exists in the field and link it directly with a market opportunity. In our experience, research must begin by observing actual challenges in hospital and industry. Not only what is scientifically interesting, but what is urgently needed. By working early with hospital engineer and industrial distributor, we could design solutions that were technically sound and commercially viable. As highlighted by Masirova et al. In 2020, successful medical device innovation requires aligning clinical need, technical feasibility, and business viability from very beginning. Okay. The second principle is to build a multidisciplinary team from the very beginning. In medical device commercialization, technical skill alone are not enough. You need engineer to design the system, business expert to define the market strategy, finance specialists to manage cost and funding, and legal advisor to handle certification and intellectual property. By combining these diverse competencies early, we can develop products that are technically robust, financially sustainable, and legally compliant, and ready to enter the market smoothly. Okay. The third principle is about funding strategy. In our experience, strong financial planning determines whether an innovation can reach the market. We successfully obtained around 3 billion rupiah in research grant over 3 years with support, prototype development, pilot testing, and certification. Government programs such as Kedereka and Ristek Deti Innovation Grant provide excellent opportunities if we have a proposal aligned with national healthcare priorities and include industrial partner. The key is to design funding as a roadmap from lab to market, not just to publish research, but to prepare a real product ready for hospital. The fourth and fifth principle relate to technology selection and product evolution. We learned that focusing on medium complexity technology, such as IoT monitoring and automation, offer the best balance between feasibility, cost, and impact in Indonesia. We also adopt an iterative development strategy. Okay? Start simple, enter the market early, then upgrade gradually. For example, Algis IoT began as a conventional alarm, the first version, evolved into a digital version in second version, and then later into a cloud-based IoT system for the third version. This stage approach reduce risk, accelerate adoption, and ensure that each version deliver real value to the users. Okay. The sixth principle is to start with not patient contact device. This is our strategy. For you innovator, this approach simplifies certification and shorten the time to market. Device such as hospital monitoring or infrastructure automation system have lower regulatory risk compared to diagnostic or therapeutic equipment. Our own product, the Algis IoT gas monitoring system and the IoT-based modular operating theater, focus on hospital infrastructure rather than direct patient contact. This strategy allows us to move faster, gain credibility, and build experience before expanding toward more complex medical device. Okay, after several years of development, we have successfully commercialized two IoT-based medical device, the Algis IoT Hospital Gas Monitoring System and Modular Operating Theater Automation System. These achievements were possible through close collaboration between university researcher, industry partner, and hospital. From our journey, 6 key lessons stand out. 1, start from real problem and market needs. 2, build a multidisciplinary team. 3, plan funding strategically. 4, choose feasible technology. 5, develop product iteratively. And 6, the final is begin with non-patient contact device. Together, these principles show that academic innovation can reach the market and make a real impact on healthcare system in Indonesia. In conclusion, our experience show that research commercialization is possible and impactful when it grounded in real needs, supported by the right team, and guided by a clear roadmap from lab to the market. Academic innovation should not stop at publication. It should continue until the product benefits society. I would like to express my sincere appreciation to the Ministry of Higher Education, our industry partner, PT Putra Medical Tech Indonesia, and Universitas Islam Indonesia team for their dedication through this journey. Finally, thank you to the IB Tech 2025 organizer and IEEE community for the opportunity to share this story. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Let's give him a warm applause to Pak Firdaus who can help me to arrange the time. Okay, ladies and gentlemen, we have 15 to 20 minutes for Q&A. So there is still no question on the Zoom chat. So if everyone wants to ask here, please raise your hand, mention your name, and direct to whom the question you want to ask. Anyone, ladies and gentlemen, please. Don't give me difficult time. Okay, please give the microphone to him. Oh, okay, okay. Please, you can start the question.
Okay, thank you. Thank you for all presenter. This is I will ask question for Prof. Yuan Lee. We have Indonesia. We have very much 280 million citizen. When we implementing like, do you have any direction or what experience in Malaysia for adopting a wearable device for digitalization of health for each patient? Do you have any when in COVID, Singapore use wearable device to track each other citizen? This is a good idea, but we cannot do that in Indonesia. So because the price of the device itself. So from in diabetes object, so how many costs it will be in market, because if it should be affordable for developing country like Indonesia. So do you have any direction for next future to being mass produce of this device? I interesting with that monitoring diabetic in attached on patient body. So my question is, how you have a suggestion to a country like Indonesia, we have with many possible patients that have increasing in diabetes. Thank you.
Okay, thank you. Okay, please, Dr. Aileen.
Thank you for the question. If I understand you correctly, because you are concerned about the cost of the device, and we can't have every patient having one at home. Actually, this is, I think this problem is the same for all low middle income countries, similar for Malaysia as well. Not many patients actually can afford to have one at home. But the hopeful thing is, actually the cost of the materials are not too expensive. I think it is now selling very expensive in the market because of the clinical test. You know, for companies who did the research, they spend so much money on the research. So when it was first introduced, rolled out into the market, of course the price is a bit high. So the continuous glucose monitoring patch is a bit expensive now, simply because it is rather new. But I envision the price will only go down, just like our blood pressure monitor, everything. As it becomes mass-produced, it becomes cheaper. The same brand, because my student is a Chinese national, he bought the same brand in China at less than half the price. But because the stock finished, so he had to replenish the stock in Malaysia. So he found the same product selling in Malaysia at a much higher price. So pricing is actually controlled by the market or by the company who brings the product in. But the cost itself to mass manufacture is not that high. And I hope and I believe that if more companies come into the market, the price will only go down, then it becomes accessible to all. I hope that answers your question.
Okay, so ladies and gentlemen, this is a kind of opportunity for every one of us, that if we can bring cheaper technology to this kind of problems, then the benefit will be higher. And if we connect to what Pak Firdaus said, this is already, we define a problem now, so after this conference you can propose a good proposal for it. Okay, is this answer your question, sir? Okay, Thank you. Any other question, ladies and gentlemen? We still have plenty of time to discuss. While Dr. Eileen mentioned something, I directly try to find the price of the pads. I agree with him because, please, I know that this continuous pads is now become more common, also not only for patients with glucose in Indonesia, but for people who are a little bit more serious in doing sport, to monitor if they have a sudden drop in glucose while doing a training, for example. Okay, next question, Pak Hendra. Yeah.
Check. Thank you very much. I have a question to Dr. Eileen regarding the system that you propose in the presentations. I think there is an issue, the privacy issue, because in the medical data record actually is not for publish. How about these issues in your system? Is there any regulation from the government to make sure that this data is still private? And the second question is about the I think that the system that you propose, it will need a very advanced of the telecommunication system. What do you think about the 5G or 6G? Is it enough for that kind of support your medical field in this your system? And then my question is to Osa Sensei. Sensei, regarding this, your research, is the ethical clearance is required for developing the artificial heart in Japan? Do you think that the ethical clearance will make the development of the artificial heart is kind of
difficult? No?
Yeah, the barrier to develop the artificial heart. Do you think is the barrier, or actually this is the one step that you need to take care before you go to the artificial heart research? Thank you.
Okay, thank you, Pak Indra. Okay, Dr. Eileen, you can answer the question first.
So regarding the medical records, in Malaysia, a few years back, we were working with the hospitals because I was starting on the heart arrhythmia project, and we want to develop our own monitoring device, which has to go to the that means to the cloud. So we were told that the rule of the hospital is they must maintain their own server. So if it is, say, Sunware or IJN, they must have their own server belonging to that hospital, and the patient data can only be stored there. So it cannot be shared. So that is the requirement by the government, and also I think the guidelines of the hospital. And that is why the data in Malaysia is very siloed, because the different private hospitals will store their own data and it is not allowed to be shared. But in Singapore, when it becomes mandatory, becomes a legislation that the government opens up and mandate everybody to share the data, then only we get to have this consensus that everybody has to follow the same protocol, everybody has to share their data. And for me, it is very important, because if we imagine an epidemic or like COVID happening again, we need this kind of data across the nation, so that the government can simulate, if I do this here, what will happen to the rest of the country. So when that data is connected, we know where are the critical patients, you know, where is the aging community, which area actually requires more support, much more easily as compared to this siloed database. And I'm looking forward to that day. Okay. And because we have these standards, like you say, ISO standards for data protection and interoperability, if we follow the release protocol as required by the standards to keep data secure, I believe the digital systems like banking, right? Everybody is using banking now. but we can seamlessly pay. Last time it was quite difficult to pay across banks, but now because of the standardization and then the seamless integration between banks, I think we can achieve that similarly with the medical records. That is my opinion. I hope I answer your two questions. Oh, and the 3G and 6G, in my personal opinion, it depends on your application. If we look at robotic surgery, like automated, somebody in US controlling the robotic surgeon in Malaysia, then of course we will need the faster signal, right? Especially if you are doing microsurgery. But if it is patient telemonitoring, discussing with doctors, maybe that is not so critical.
Okay, so can I say that actually in Malaysia now, the rules from the government about the data is still not as open as in Singapore? Or now in Malaysia is already open?
I don't recall it being open yet. That means it's depending on each hospital. So each hospital will build their own database and protect their own database. There is no consensus as to we must share.
Okay, so still similar with in Indonesia to some extent, Pak Hendra. Because what you mentioned, what happened in Singapore, I think it should be the new standard in the future. Okay, Dr. Osa, can you hear us?
Yes.
Do you recall the question from Pak Hendra, or Pak Hendra asking about the ethical clearance? So he was asking whether in your research about artificial heart pump, ethical clearance is a must in the sense that you have to take care of it before you start the research, or is it something else in your perspective? Maybe you can share a little bit about it.
Thank you very much for your question. There are limitations to development at the university in terms of manufacturing costs and the development speed. However, even if there is a social significance, collaboration is difficult if companies cannot monetize, making it difficult to create companies to conduct joint research, collaborative research. Obtaining grants is also difficult for such kind of ventricular assist device development. The market for pediatric ventricular assist devices is particularly small, so making collaboration extremely difficult. However, I believe that in order to make this reality, we must continue to work continuously at the university with a collaborative researcher and my students. Is it okay?
Pak Indra? Should be enough? Okay, thank you very much, Dr. Osa. Okay, am I allowed to have one more question from the organizer? I think so. So one last question, anyone? Should be enough? Okay, I think every one of us is a little bit hungry now. So ladies and gentlemen, give a big warm applause to all our keynote speakers who already gave us a very interesting talk. So I will not conclude anything because I believe that you can take your own notes about the diversity of the talks. And of course, during the lunch session, you can directly approach our all keynote speakers or email Dr. Osa if you still have questions or interesting next topics to be discussed in the future. And with this, I end these keynote speakers, and I will give back the microphone to the organizing committee, and thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Once again, let's give round of applause for our keynote speaker and moderator. So we would like to thank you very much, our gratitude for Mr. Sisdarmanto Adinata for guiding discussion so clearly and effectively, and we want to beg for our keynote speaker and moderator, give you back. Take your seat right now. Thank you very much for our keynote speaker, Dr. Aileen Suliming from University Technology Malaysia, Dr. Ahmad Arifin from Institut Teknologi 10 November Surabaya, Indonesia, dan Mr. Masahiro from Ibaraki University Japan, and especially for Insinyur Firdaus from Universitas Islam Indonesia for their insightful presentation in this event. Thank you very much for all participation, for joining, for the active engagement during session Q&A. So ladies and gentlemen, in the next we have lunch break. So the which will take place at the FTI second floor, FTI corner. However, before we continue our the lunch and prayer break, there will be several announcement regarding for parallel session after this break, which will begin at 1 p.m. in the room and online. Therefore, we kindly invite all participation both online and outside to adjust accordingly. The information for participation join with us offline, we have some group. Offline group 1 will be held in learning space 1, first floor, with the session chair by Dr. Odi Virgantara Putra Eskom MT. Offline group B will be held in learning space 2, first floor, with the session chair by Muhammad Arianto, PhD. Offline group C will be held in audiovisual 1.10 room, first floor, with the chair session by Ms. Swatmi Murnani STMN. So participation joining with us online via Zoom. Online room 1 with the session chair by Mr. Afin Muhammad Nursani STMT. Online room 2 with the session chair by Mr. Insinyur Tito Yuwono. Online room 3, session chair by Ms. Elvira Sukma. And then online room 4 with the chair by Ms. Ida Nur Cahyani. And the last room, online room 5 with the Ms. Almira Budianto. So ladies and gentlemen, after this, we can to take lunch before and then, sorry? Okay. Okay. And then ladies and gentlemen, we have some door prize and maybe, prize from the commit for our keynote speaker. The first for Dr. Ang Lee, please come join us on this stage big. Okay, Dr. Aileen from University Technology Malaysia. Okay, will be give for the chair of the 4th International Biomedical Instrumentation. Yeah. And the second, okay, Dr. Arifin, please come join with us on this stage to receive our souvenir from Universitas Islam Indonesia will be given by Mr. Firmansyah in this session. Please give round of applause for Dr. Iling Suliming from University Technology Malaysia. And the second souvenir gift from Universitas Islam Indonesia, our second keynote speaker, Dr. Ahmad Arifin STMN from Institut Teknologi 10 November, Surabaya, Indonesia. Once again, let's give round of applause for them. Thank you very much. So ladies and gentlemen, in the next agenda we have lunch break and zuhur prayer. Maybe you can to have lunch break in the FTI corner second floor after this. Thank you very much, and we come to expect you to back meeting at 1 p.m. right now. Thank you very much. Okay, once again for all participation who already in this room, maybe you can to have for lunch break, which will be take in the FTI corner, the second floor. Maybe the commit can the direction in there until we have 1 p.m. We can to continue our agenda is the parallel session after this in this room.
can click off this.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome back to 4th International Biomedical Instrumentation and Technology Conference 2025. Wow, it was amazing. I think you have participation have study in this parallel session, right? I think yeah, the participation good, information, knowledge, have knowledge. And then, ladies and gentlemen, next we will watch together the teaser video of after movie from the series The Fourth International Biomedical Instrumentation and Technology Conference 2025 activity. Enjoy the show. Let's give a round of applause for the video teaser after movie The Fourth International Biomedical Instrumentation and Technology Conference 2025. The video is very, very amazing, interesting, and beneficial for us, right, everyone? Okay, so ladies and gentlemen, the next agenda we have the announce on the best paper and the best presenter award. Wow, who do you think will be the winner? Who could it be? Wow, I think the participation, the presenter can wait the result. Okay, ladies and gentlemen, but before we announce this award, let us the first listen to closing remarks by the chair of the Fourth International Biomedical Instrumentation and Technology Conference 2025. Please welcome and give a round of applause for Insinyur Firmansyah Nur Budiman. The stage is yours.
Cek. Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, distinguished guests, respected speakers, participants, and all colleges. I hope that you are still with us, although we have lost a lot of people here. There is only a few people, no problem. As we come to the end of this remarkable conference, it's my great honor and pleasure to deliver the closing remark on behalf of the organizing committee. Today we have witnessed an inspiring exchange of ideas, thoughtful discussion, and the formation of new collaboration that we will no doubt continue to grow long after this event concludes. Of course, an event of this magnitude does not happen by magic. It is the result of countless hours of dedication and tireless work. My deepest, most sincere gratitude goes to the backbone of this conference, which is the entire organizing committee. So please give a warm applause to the organizing committee. Thank you very much. To every person on the committees for managing the submission, coordinating the logistics, assisting our speakers, and ensuring the smooth running of the every session, your hard work and commitment have made this a truly memorable and flawless event. Thank you. Please join me in round of applause again for the committee. Thank you very much. I must also thank our exceptional session chairs, our dedicated reviewers, and of course, every single presenter who shared their valuable research with us. Now, as we prepare to leave, our work does not end here. The true measure of this conference success will be what you do next. I encourage you to take the ideas, the connection, and the inspiration you have gathered and apply them with renewed vigor in your lab or in your institution. Let the collaboration started here be the basis for your next major grant proposal or publication. We look forward to seeing the result of this new collaboration at the 5th International Biomedical Instrumentation and Technology Conference, which will be held 2 years from now. Please mark your calendars and plan to join us again. Until then, travel safely. Thank you for making this a landmark event. The 4th International Biomedical Instrumentation and Technology Conference is now officially closed. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. I think for Mr. Firmansyah can stand by on the stage, because after that we have to announce the best paper and best presenter award. Okay, ladies and gentlemen, please be wait. Okay, we want to announce the first we have best presenter. Okay, maybe the committee give some sound wording. Yeah. Okay. Who could it be? The winner of the best paper, the first. The best presenter from Group A goes to Mr. Riza Shah. The title is Beyond Classical CNS, Quantum Classical Hybrid Network, Initiative 90H Occurrence in Breast Cancer Classification. Okay, the winner can up on the stage. Okay, from Group C, the best presenter. The best presenter from Group C goes to Mr. Raja Busman. The title paper is Assessment of the Osteochondritis in Good Change. Congratulations, Mr. Wow, it was amazing. And the best presenter from Zoom 1. Okay, from Zoom 1 goes to Mr. Yasha Saleh. The title presenter is Finite Element Analyze Madibur. Congratulations for the Yasha Saleh. And the best presenter from Zoom 2, we have Pravalika Saladi. Congratulations, Pravalika Saladi. The title is Anatomical Plane Classification for Fetal Head Ultrasound. Congratulations. And the best presenter from Zoom 3. We have Mr. Bagus Nupriyanto. Congratulations for Mr. Bagus Nupriyanto. And the best presenter from Zoom 4, we have Nur Zaswa Nasahar. Congratulations. And the last best presenter from Zoom 5, we have goes to Alice Raputri. Congratulations for Alice Raputri. And then we have the winner of best paper. I mentioned one by one. The first goes to Nur Syasyawa Sahar. Congratulations. And the second we have Bagus Nupriyanto. Congratulations. And the last we have the best of the best paper. Wow. We wanna wait after this. Okay. Best of the best paper goes to Nur Syawana Sahar. Sorry, I want to replay again. Goes to Agung Nugroho Setiawan. Congratulations for the winner of this event. Congratulations. And then for Mr. Firmansyah, please give congratulations for the all winner who stand by in here on the stage. Okay, yeah. Mr. Firmansyah can be give some souvenir for all the winner in this event. Okay, therefore we would like to respectfully invite the chair of IB Tech 2025 to come up in this stage and give certificate of appreciation, and especially for this event, give souvenir to the all winners. Don't worry, everyone. The certificate will be sent each receive an email after this event. So thank you very much. Okay, once again, please give a round of applause for all the winners. Okay, thank you very much, everyone. Distinguished guests, excellencies, ladies and gentlemen, Alhamdulillah, with the conclusion of the announcement session, we have reached the end of the first day, the 4th International Biomedical Instrumentation and Technology Conference 2025. It has been a fruitful discussion and productive time. We hope that you found the presentation insightful today. So on behalf of the organizing committee, I am Hassan Fadli, would like to express our gratitude for your attention and participation. May you always have blessed with the health, happiness, and continued success in your endeavor. We would like to express our gratitude too for keynote speakers. Thank you very much for coming here. Guests and participation will join online and outside via Zoom meeting. And thank you very much. Let us close this event together by reciting Hamdalah together. Alhamdulillahirabbil alamin. It's been a wonderful evening with all of you guys. We are signing out right now. Bila taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.